earlier from the results we did from Cauchy's theorem. Is that okay? Okay. So, it's all about looking at the class equation and arguing carefully from that. Okay, so we can now go for, I think we can go for the first Sylow theorem now. So the same remarks, apply from the setup we did in the first lecture today. We're talking about the group acting on itself via conjugation, and then counting the elements of the group through the orbits of that action gives rise to the class equation. So Cauchy's theorem, we've seen Cauchy's theorem from today. Cauchy's theorem basically says that if P divides the order of G, then G has elements of order P. Or equivalently, and it's probably best phrased this way, or equivalently, G has a subgroup. It's a subgroup of order P. Now, subgroup of order P, elements of order P, they're equivalent. The subgroup of order P, it has to be cyclic groups, so all the non-identity elements in that subgroup of order P, and any element of order P generates a cyclic subgroup of order P. But it's probably best to think in terms of G having a subgroup of a certain size, because that's the way we need it for the first Sylow. So this is all very well for just P dividing the order of G and a subgroup of size P, but it could be that P squared divides G or P cubed divides G. G doesn't just have to have P as a factor of multiplicity 1, it could have higher multiplicity. So the first Sylow theorem, says, well, if you've got P to any power dividing the order of G, by implication, the order of G is finite. I wouldn't talk about an integer dividing infinity. So by implication, the order of G is finite. Then G contains a subgroup. G contains a subgroup of this order, of order P to the R. Now, that's not the same as saying it's got elements of order P to the R. If it had an element of order P to the R, then yeah, that would generate a cyclic subgroup of size P to the R. But this subgroup that we're talking about might not necessarily be cyclic. It might come from an element itself. Okay. And then what we're going to call, what will be called Sylow P subgroups. Sylow P subgroup will be one of these kind of things where the exponent R is the biggest it can be for that particular group. But that's referred to in the second and third theorems. So this is obviously easily understand this as a generalization of the Cauchy's theorem that we proved this morning, and it's proved in somewhat similar way, focused doing an induction proof and making use of the class equation where appropriate. But to achieve the more difficult induction step, we have to talk about quotients or factor groups as well, and do something which is explained quite quickly there in the notes, and something I'll expand upon here. Performing it carefully, knowing exactly what the factor group homomorphism does, and what the sizes are of things in the factor group compared to things in the original group. Yeah. So we will induct on. We will do induction on the size of G. So let's suppose G, let's use N for the size of G. The basic, like the smallest size that we'd have to consider is where n is equal to p itself. Okay, could be because that's the smallest size of group for which this setup is true, and then the theorem is true. Theorem is trivially true because G will be a subgroup. I mean, the only power you can have dividing the size of G will be p to the 1, and then just G is a subgroup of itself, so it's a subgroup of size p. So the theorem is trivially true, just as in the proof of Cauchy's theorem that we saw earlier today. But there's nothing to prove really, because the subgroup we're asking for is just provided by G itself. Okay, so now assume the theorem is true for all groups of size, or of order, I should say, same thing, size, but of order strictly less than this n, whatever n is, strictly less than n, where, well, just that the theorem is true for all of these. Okay, so where some power of p divides the size of these smaller groups, and we're assuming that they all have then subgroups of the required size. So again, we return to the class equation. I know we've written it out quite a few times, but you know, it's just good to write it out again. Practice it. So it's the size of G is the size of the center plus then a collection of indices. These are the size of the orbits under the conjugation self-action. Okay, so the same explanation here. Z G is the center, and x1 through xk are representatives from the non-trivial orbits of the action conjugation, and these are essentially the size of each orbit, but represented here as the index of the centralizer subgroup in G. Which, remember, because we're dealing with finite groups, these indices are simply the size of G divided by the size of that centralizer. So now the different cases go slightly differently to the proof of Cauchy's theorem. So the simpler case to deal with. Simpler case is when there is some I, an I from 1 to k, from this set of i's between 1 and k, where p does not divide the index of the centralizer cxi in G. So if one of these terms in the class equation is not divisible by p. But remember, we can always write the size of G as the size of this stabilizer multiplied by this index here. That comes from Lagrange's here. This index, remember, is the number of cosets of this subgroup, and all of these cosets have the same number of elements in them. They all have this number of elements in them, and they partition set G. So when you multiply these two together, the size of each of the cosets multiplied by the number of cosets gives you the size of G, because that's all the elements of G. So if this I is special, where P does not divide this factor, so this factor because this is some kind of factorization of the size of G. There's no factors of P here, but we're assuming that there's R factors of P at least in G. So that means if P to the R divides the left-hand side, but P does not divide this, it must be that P to the R divides this, okay? Because if there's a factor of P to the R here, where are those P's here? Well, if none of them are in this part, they must all be in this part, okay? So this implies that in this case, P to the R divides the size of this centralizer. Divides the size of this centralizer. But then that's going to be, this centralizer is a smaller subgroup, is a smaller group than G. It's a proper subgroup of G. So that means it's covered by the induction hypothesis. So CXI, the centralizer CXI, will contain a subgroup of size P to the R. Okay. And this is strictly less than the size of G. So by the induction hypothesis, the centralizer contains a subgroup. Contains a subgroup of order size P to the R. That's a subgroup of centralizer, so it'll be a subgroup of G. Okay? The centralizer is a subgroup of G. So, and this is the required or a required. This is the asked for subgroup. Asked for subgroup of G. That's just in this simpler case. When it happens that one of these terms from the class equation is not divisible by P. So the general case then, the cases we haven't dealt with, is when this can never happen. So that all of these terms are divisible by P. Okay. So otherwise we assume that for all I between 1 and k, P divides this index term. Okay. Now, and then this is where we appeal to the class equation. So now we're in this situation where P divides each of these terms in the class equation. P certainly divides G, because we know that P to the R divides G. So at least, we definitely know that P divides G. So P divides G, P divides each of these, therefore P must divide the size of the center. Okay. So by the class equation, P does divide the center. The size of the center. And okay, the center, remember, is an abelian group, but we've got Cauchy's theorem now, so there's going to be a subgroup of the center of size P. Okay, we're trying to get this subgroup, the special subgroup of G, size P to the R, but we're going to make an argument now in factor groups, and we're going to use this special element from the center. Okay, so by Cauchy's theorem, which we proved earlier today, or the fundamental theorem of finite abelian groups, fundamental theorem of finite abelian groups in the previous chapter, since ZG is an abelian group. ZG has an element of order P. Let's call it G. G, say. It has an element, little g, of order P. And what we're doing here, remember, we're in a proof by induction. We've got this simpler case out of the way where you get the result fairly easily because one of the subgroups, which is size smaller than G, is divisible by P to the R, so therefore that's covered by the induction hypothesis. If that's not the case, if we can't point to a subgroup of G, whose size is divisible by P to the R, then we've got to somehow transfer ourselves down to a smaller group. And that's going to be the idea of a factor group. Transfer ourselves down to a smaller group where we can use the induction hypothesis. Okay, and we're going to do it by taking a quotient using this special element G. So consider N. So consider N, which we define as the cyclic subgroup generated by G. Okay, by this element little g. This is a subgroup of the center. So of course, it's also a subgroup of G. Now, if we're going to use this to form a factor group, we need to know that it's a normal subgroup. Now, what's the definition of normal subgroup again? Normal subgroup, the definition is that left coset equals right coset. Okay. So recall, N is normal in G. Normal in the group G means the X in G, the left coset Xn is equal to the right coset. But you see, N is a subgroup of the center. The center is extremely special. It consists of elements that commute with everything in G. Okay, so N is a subgroup of that. Maybe all of it, maybe not. But it's a subgroup of it. So everything in N commutes with everything in G. Okay. So N consists of elements from the center. So it's true that for every X in G and for every little n in N, X times N is equal to N times X. And we don't need that. You don't need exactly this for the subgroup N to be normal. You just need this kind of commutativity with X on the set level. But it's true, it's a lot stronger than that. It's actually true on the element level, taking elements from N. These are special elements. They come from the center. So they commute with any element from the group. So that implies that for every X in G, X times N, the left coset will be equal to the right coset. So N is normal. N is normal, and we can form the factor group. I kept saying quotient group there, but Judson's book uses the terminology factor group. The factor group G mod N. Now, this is certainly a smaller group than G, because we're factoring out by something non-trivial. Is N non-trivial? Yeah, because N is generated by this element little g. This element little g has got prime order, this order P. So N is a non-trivial subgroup. So you're definitely forming a smaller group. So notice that the size of the factor group is certainly smaller than G. So it will be covered by the induction hypothesis. In fact, it's equal to, in fact, yeah, the order of the factor group is equal to just the quotient of the sizes, and n has size p. That's the size of G divided by p. So in the assumptions of the theorem, the statement of the theorem, we're assuming and even further, we're assuming that p to the r divides g. P to the r divides g. But the factor group has size g divided by p. So if we know that p to the r divides the size of g, here we're cancelling out one factor of p. So all that we know, the strongest we can say, is that p to the r minus 1 divides the size of the factor group. Isn't that right? Because we've chopped away one factor of p. Okay, it could still be that p to the r divides this if this p to the r was not maximal up here, if there were further factors of p that divided into the size of g. But without knowing that, if all we know is that p to the r divides g, then if we move to this smaller group by dividing out by p, the size of n, then all we can say is that p to the r minus 1 divides this. Okay? But the point is, because this is a smaller group, this is covered by the induction hypothesis. So the induction hypothesis says that G, this factor group, let's see what letter he uses. He uses a H. This factor group has a subgroup H of order p to the r minus 1. Now it's this subgroup H. We're going to somehow associate the subgroup that we need to prove the theorem. We need to get a subgroup of G of order p to the r. We're going to do that using, it's basically the existence of that subgroup of G of size p to the r is going to come from the existence of this subgroup H of the factor group. Okay. So now here, after talking about H, he just gives another sentence and says, therefore, there's a subgroup of size p to the r of G. But we just have to recall a little bit here. So recall the factor group homomorphism. Homomorphism phi. So when you construct a factor group, you've always got, there's this canonical or this homomorphism from the original group to the factor group. That sends, and this is defined by sending phi of little x to the left coset xn. Okay, remember the factor group consists of, is the group generated by the cosets. Left or right cosets, doesn't matter because they're the same. So the definition of this homomorphism is phi of an element little x from G. It sends it to the coset x dot n. Now, if n is non-trivial, if the size of n is strictly greater than 1, you can factor out by the trivial subgroup, the subgroup just consisting of the identity. But then the factor group is just going to be isomorphic to the original group, because if you're talking about cosets of the trivial subgroup, but they are just correspond to elements of the original group themselves. So you're not really achieving anything. It's like dividing by 1. When you divide an integer by 1, you don't do anything, you just left with the same integer. But if the subgroup that you're quotienting out by is non-trivial, then n is not injective. It's certainly not 1-to-1, but it's many-to-1. It's not 1-to-1, it's many-to-1. In fact, it will be exactly the size of n to 1. Meaning that for any particular coset in the factor group, there will be the size of n different elements in G that get mapped to that by the quotient homomorphism. I.e., every element of the factor group, i.e. coset of n, will have this number, size of n, pre-images under 5. Remember, a pre-image of something is like, you got something over here, a pre-image is something in the domain that gets sent to that element by the homomorphism. So basically, when you form a factor group like this, you're basically collapsing the group G down. You're losing information about the group G, but you're collapsing it down in this many-to-one fashion. And the many is given by the size of the group, the size of the group that you're factoring out by. Now, if you look back in the chapter on factor groups, there was a important one. Sorry, this is the chapter on homomorphisms. Chapter 11 on homomorphisms. We look back here. Well, it's maybe not. Yeah, okay, the correspondence. So this was in where you had n being a normal subgroup of G, and you formed the factor group Gn. The correspondence theorem tells us that subgroups of Gn are in 1-to-1 correspondence between subgroups. Okay, we're using the same letter H. In what we're in the proof we're developing there, H is a subgroup of the factor group. Here in this statement, H is a subgroup of G. So it's a different use of H. But subgroups of the factor group correspond under the action of the quotient homomorphism to subgroups of the original group that contain n. Okay. And this correspondence is through the factor group homomorphism. In fact, we already proved that for homomorphisms, that if you've got a subgroup in the codomain, when you take its inverse image, it's a pullback, so to speak, that is a subgroup in the domain. Okay, so this is just a bit of a reminder about factor groups and the homomorphism associated to it. So we can say by the correspondence theorem, or just properties of homomorphism, really. the inverse image. Remember H. What is H? H is a subgroup of the factor group. So its inverse image under the factor group homomorphism is a subgroup of G. It's a subgroup of G containing N. I don't think we actually need the fact that it contains N. I'll just put containing N in brackets there, but I don't think we're actually going to make use of that. Question is, what size does this have? So consider the order, the size of phi inverse of H. So how big is phi inverse of H? Well, how big is H? H is a subgroup of G mod N, which is size p to the r minus 1. Yeah. Phi inverse of H, remember the definition of inverse image of something. Inverse of image, something is just defined to be the set of all x's in G, such that phi of x is an element of H. That's what you mean by the inverse image of a subset of the codomain of a map. It's just everything in here that got sent into that subset. But you see, we explained here the many-to-oneness of the map phi. It's a size of n to 1. Okay, so onto each element in the codomain, it maps size of n different elements over here. Now the size of n here, if you look back, is p. Okay, so p is phi is a p to 1 map. Okay, p was the size of n. N was the cyclic subgroup generated by an element of order p. So if the size of H is p to the r minus 1, every element in that has p different pre-images of it under the map phi. So you're multiplying by p in effect. So the inverse image of H will have size p times the size of H. Okay. So the size of phi inverse of H, because phi is p to 1, it will be p times the size of H, which is equal to p times p to the r minus 1, which is equal to p to the r. And because phi is a homomorphism, the inverse image of a subgroup in the codomain is a subgroup of the domain. Okay, that's what the correspondence theorem tells us. So phi inverse of H is the required subgroup. The required subgroup of G of order p to the r. So that's the culmination of the induction step. We assume that we observed trivially that the theorem is true for the base case. That was groups of size p, the smallest groups that it applies to. And then we assumed it was true for every group of size strictly smaller than our focus group G. And now we've been able to deduce that it's true for G, okay, by appealing back to that induction assumption. Okay. So the theorem is true for groups G of size n. So therefore, by induction, it's true for every integer n. So it's true for all finite groups. It only applies to finite groups because you're talking about where the size of the group is divisible by some power of p. So that doesn't make any sense when you're talking about finite groups. So that proves it, okay? So again, it's another assertive positive statement. But based on knowing the only thing we know about the group is the size of the group. Okay. Okay. Now we've built up a lot of the theory of group actions and the class equation, but it's using no more information than the group except for its size, but yet it can assert that if the size is divisible by a power of some prime, it must have a subgroup of that same size. Okay. So that's it stands out as quite a powerful result. Okay. So that's the end of that proof. So we're going to come to the second and third. The second and third theorems, the second and third Sylow theorems concern Sylow, so-called Sylow P subgroups of G. These are subgroups of order P to the R, where P to the R divides the order of G, and R is maximal. Okay, so P to the R is the full power of P that there is in the prime factorization of the size of G. Okay, those are so-called Sylow P subgroups. They're the largest P subgroups that G has. We know these exist by the first theorem. First theorem doesn't say anything though about the number of them that there are. Okay. So the second and third Sylow theorem concern these subgroups of these, how they relate to each other, and restrictions on the number of them that there are, and restrictions on their number. So how the different Sylow P subgroups of a particular group relate to each other. They're all related by this operation of conjugation. So conjugation rears its head again. And we've got very interesting divisibility and congruence type restrictions on the number of them that there are, which in many examples allows us to deduce exactly how many of them that there are. Okay, so we're going to continue to talking about this action of conjugation. For Cauchy's theorem and Sylow, and the first Sylow theorem, we're talking about the group G acting by conjugation on itself. The second and third, it's still conjugation, but now we're going to be doing not conjugation on the elements of G, but conjugation on the Sylow P subgroups. So not only moving the elements of G around by conjugating by elements of G, but now by moving subgroups around. And that will allow us to assess and tackle the relationships of these different subgroups to each other through the operation of conjugation. So I might stop there for this afternoon, unless there's any questions or clarifications you wanted. Anything from that? Is that okay? Okay. So in the next couple of lectures, then we'll tackle the proofs. I mean, it's not a huge amount. I mean, I think it's all just on one page, just on the next page there, 243 in the notes. But there's a lot of stuff compacted there. So I want to give a good explanation of that in the next lecture. So I'll see you then, and that will, after that next lecture or two, that will be the kind of the end of all the theory, and then we're just going to go to town on the exercises, lots of kind of workshop activities. Is that okay? Okay.